Hello and welcome to Chapter 32, The Atom and the Quantum. Now that we've kind of established quantum theory with photons, we are going to talk about how that theory interacts with our idea of the atom that we talked about earlier. First, we are going to talk about how the atom is made up as a nucleus and as an electron cloud in the edge of it. So the first thing to bring up is Rutherford's gold foil experiment. In Rutherford's experiment, a beam of positively charged particles, alpha particles, which we're going to get into in the next chapter, from a radioactive source was directed through a sheet of extremely thin gold foil. Because alpha particles are thousands of times more massive than electrons, it was expected that the stream of alpha particles would not be impeded as it passed through the sea of electrons. This was indeed observed for the most part. Nearly all alpha particles passed through the gold foil with little or no deflection and produced a spot of light where they hit a fluorescent stream beyond the foil, but some particles were deflected from their straight line paths as they emerged. A few alpha particles were widely deflected, and a small number were evenly scattered backwards. These alpha particles must have hit something relatively massive, but what? Rutherford reasoned that undeflected particles traveled through empty space in regions of the gold foil, while the small number of deflected particles were repelled from extremely dense, positively charged central cores. Each atom, he concluded, must contain one of these cores, which he named the atomic nucleus. Another important development in the development of atomic theory is cathode rays. So we've known about electricity in general since Benjamin Franklin, but Sir William Crookes, an unorthodox English scientist who believed he could communicate with the dead, set up this experiment called the cathode ray tube. He is better remembered for his Crookes tube, which is what we now call a cathode ray. A sealed glass tube that contains gas under very low pressure and has electrodes inside the tube near each end, the forerunner of today's neon signs. The gas glowed when the electrons were connected to or when the electrodes were connected to a voltage source, such as a battery. Different gases glowed with different colors. Experiments conducted with tubes containing metal slits and plates showed that the gas was made to glow by some sort of ray emerging from the negative terminal, the cathode. Slits could make the ray narrow, and plates could prevent the ray from reaching the positive terminal, the anode. The apparatus was named the cathode ray tube, or CRT. When electric charges were brought near the tube, the ray was deflected. It bent forward positive charges and away from negative charges. The ray was also deflected but in the presence of a magnet. These findings indicated that the ray consisted of negatively charged particles. In 1897, then, the English physicist Joseph John Thomson showed that the cathode rays were particles smaller and lighter than atoms. He created narrow beams of cathode rays and measured the deflection in electric and magnetic fields. Thomson reasoned that the amount of the beam's deflection depended on the mass of the particles and their electric charge. How? The greater each particle's mass, the greater the inertia and the less the deflection. The greater each particle's charge, the greater the force and the greater the deflection. The greater the speed, the less the deflection. From careful measurements of the deflection of the beam, Thomson succeeded in calculating the mass-to-charge ratio of the cathode ray particle, which was named the electron. In 1909, a dozen years after Thomson's mass-to-charge experiments, American physicist Robert Millikan carried out an experiment that enabled him to calculate the numerical value of a single unit of charge. In his experiment, Millikan sprayed tiny oil droplets into a chamber between electrically charged plates into an electric field. When the field was strong, some of the droplets moved upwards, indicating that they carried a very slight negative charge. Millikan adjusted the field so that the droplets hovered motionless. He knew that the downward force of gravity on the droplets was exactly balanced by the upward electrical force. Investigation showed that the charge on each drop was always some multiple of a single very small value, which he proposed as the fundamental unit of charge carried by each electron. Using this value and the mass-to-charge ratio discovered by Thomson, Millikan calculated the mass of an electron to be about 1/2000th of the mass of the lightest known atom, hydrogen. This confirmed Thomson's supposition that the electron is a lightweight, and it established the quantum unit of charge. Through this, we were able to come up with new atomic models. We've gone over the model of the atom over time in previous classes. So right now, I'm just going to focus on Niels Bohr's 1913 planetary model and Erwin Schrödinger's 1926 quantum model. This is because these are the models which rely on the ideal that matter is some sort of wave in order to explain the properties of the atom and the properties of the spectrums that we saw from excitation. If you'll remember from previous lectures, we established that matter also had wave-like properties and that the wavelength of this matter was dependent on the momentum of the particle that I was looking at. So this is called the de Broglie wavelength. And what the Bohr model contends is that there are only certain allowed particles, or there are only certain allowed orbital radii for particles where the circumference of that orbital radius has to be equal to some multiple of the de Broglie wavelength. So the first one has the wave go up and then down, and only do this once as it goes about in a circle. The second one has to go up and down and up and down, and then it goes around in the circle. And then the third one and the fourth one do similarly, as we can see in this diagram. What's interesting about this is that because there are only certain orbital radii, there are only certain orbital energy levels, which means that the only transitions that you can have from the energy levels from one energy level to another are from one of these orbitals to another, which corresponds to certain frequencies of light and certain energies of the electron. So these certain frequencies of light between two different orbital levels correspond to the spectrum that they were seeing for hydrogen. This also explains why the electron does not spiral into the nucleus, because it cannot have an orbital that is smaller than n equals 1, or the first de Broglie wavelength orbital. Bohr's model assumed that each electron was moving around in a circular orbit around the nucleus, much as planets move around the sun. However, this didn't end up being the case, or this isn't the most exact case that we can get. What ends up happening is that instead of having just these sinusoidal waves, we instead have waves that are the non-material matter wave amplitude, a mathematical entity called a wave function, represented by the symbol psi, where psi is the trident that you'll see in the bottom right-hand corner. The wave function given by Schrödinger's equation represents the possibilities that can occur in a system. For example, the location of an electron in a hydrogen atom may be anywhere from the center of the nucleus to a radial distance far away. An electron's possible position and its probable position at a particular time are not the same. A physicist can calculate its probable position by multiplying the wave function by itself. This produces a second mathematical entity called a probability density function, which at a given time indicates the probability per unit volume for each of the possibilities represented by psi. Experimentally, there is a finite probability of finding an electron in a particular region at any instant. The value of this probability lies between the limits 0 and 1, where 0 indicates never and 1 indicates always. For example, if the probability of finding an electron within a certain radius is 0.4, this signifies a 40% chance that the electron will exist there. So the Schrödinger equation cannot tell physicists where an electron can be found in an atom at any moment, but only the likelihood of finding it there. Or for a large number of measurements, what fraction of the measurements will find the electron in each region. When an electron's position is its Bohr energy level is repeatedly measured and each of its locations is plotted as a dot, The resulting pattern resembles a sort of electron cloud. An individual electron may at various times be detected anywhere. In this probability cloud, it even has extremely small but finite probability of momentarily existing inside the nucleus. It is detected most of the time, however, close to an average distance from the nucleus that fits the orbital radius described by Niels Bohr. I am also going to talk a little bit about Schrodinger's equation, which defines these wave functions psi. Basically, the thrust of Schrodinger's equation is that by using an operator, such as taking the derivative of psi over time, you can extract the frequency of the wave function, which times 2 pi, which when you multiply it by h bar gives you the energy times the wave function. On the other side, on the left-hand side of the equation that you see down there, you have negative h bar squared times del squared, where del is the upside down triangle, over 2m, plus the potential energy times psi is equal to the energy times psi. This is just conservation of energy because that del squared gives you 2 pi over lambda squared, which means that h bar squared times del squared gives you the momentum at any given point over 2m, which is going to be mv squared over 2m, which is 1 half m times v squared, or the kinetic energy of the wave. So the kinetic energy plus the potential energy at any given location times psi is equal to the total energy times psi. And mathematically, these end up being more complicated because the potential energy might change depending on your position in space. And if the potential energy changes depending on your potential in space, then you're not going to get that basic sinusoidal wave function. You're going to get a more complicated wave function. As you can see, the hydrogenic wave functions, which correspond to certain allowed orbitals slash energy levels, are not going to be like that sinusoidal wave that we were talking about when we were talking about de Broglie wavelength. But if you look on the right-hand side, you'll see that the probability of being in a certain space kind of looks like a smushed out probability of the de Broglie wavelength squared, which kind of looks like the orbits that you get from just a planetary model. Where this is an example of the correspondence principle, which states that if a new theory is valid, it must account for the verified results of the old theory. So we have these probability functions, and if you take the average probability, it's going to end up at the Bohr radius and look like it's just in a circle around the Bohr radius. This is also more precisely in quantum mechanics called Ehrenfest theorem, which states that if you find the average value of any quantity over this probability count, then it is going to give you the classical value that you would get. So there are only certain allowed states, and each of these states generally is going to have a quantum number, which means that it's going to have a certain allowed energy level or momentum level or some other verifiable level. But if you take the average position value of the wave function squared, then that is going to give you the Bohr radius, which is going to correspond to our older theory by the correspondence principle. And if you take the average momentum value for the probability cloud, you are going to get that classical momentum. By taking a measurement of a quantity, the probability in being of one of these quantized states, such as energy or momentum, collapses to 1. It is exactly that state. This in turn leaves other quantities open by the uncertainty principle, and a further measurement of another quantity opens up the possibility that the first quantity will be in a new state. States which are orthogonal to each other mean that you have no chance of measuring the second state after the first. However, if you have a third state that is not orthogonal to either, you can measure the first, collapsing it to the first state, then the third, collapsing it to the not orthogonal to either state, and finally the second state. This explains why the polarizer behavior we saw in an earlier chapter. This is interesting because if you look at polarization, what you expect is that the photon, when it goes through a polarizer, is going to be polarized a certain way, which means that it cannot be polarized perpendicularly to that. However, if you take a measurement and polarize the photon in a certain way, and then polar take a measurement that polarizes the photon at 45 degrees between the two orthogonal polarizers, then that means that it switches from one state to that 45-degree state, and then it switches again to the orthogonal state, which allows there to be measurements which are contradictory to each other as long as you go from one state to another state to the third state.